Good morning, guys. So I wanted to make this short video. Actually, it's going to be a series of videos, kind of to get you started on these problems from the energy unit. I'm going to be sending out a full solution manual later on in the week, but this should help you get started, give you some tips. All right, kind of the outline of what we're going to do. We're going to go through problem one, problem two. We're not going to do problem three, as that's one that I wrote, and I would like to see how you guys do on it. If you have any questions, please send me links about that. I have a solution to that I will send out as well, along with the others. Problem four, as well as problem five at the end, okay? Now, we're going to spend a good amount of time on problem two because there's been some confusion about this step here while it's rolling down. How do you calculate the force of friction? So we'll make sure to hit that in a lot of detail moving forward. Okay, well, let's go ahead and get started here with problem one. Now, a couple things to note here. If you ever see a pop up in my bottom right corner, I apologize. I'm sharing my screen with you all. Just disregard it. I'll delete it as soon as I see it if that happens. Also, I am limited to 15 minutes per one of these videos, so keep that in mind as well. I will post multiple videos to make sure this is a seamless series of notes. Okay? All right, let's get started with problem one. Okay, so we got problem one here. Now, this problem has a lot to do with calculus. Okay, I'm going to start by reading the question. A particle of mass m is moving in a conservative force field described by the potential energy function u of r. Okay, so I'm going to write this down. We got u of r is equal to a times r over b plus b over r. All right. A and B are positive constants, and r is the radial distance from the origin. This graph here represents u of r with respect to the distance r, which they've given as derivatives, or not derivatives, excuse me, multiples of r naught, which is the minimum. Okay? I'm going to go through part A for this one. All right? A says, in terms of the constants A and B, determine the following. The position, r naught, at which the potential energy is a minimum, as well as the minimum potential energy, u naught. So kind of what we're looking for here, guys, is think about this in terms of I want to figure out at the end what u of r naught is in terms of our given constants. Now, part one of this, okay, part one talks about a minimum. All right, a minimum, if you remember from calculus, the minimum of a graph happens when the derivative is equal to zero. Okay, so we're looking for the point where the derivative of u with respect to r is zero. That will give us the minimum. We're looking for this point right here. And that point is where du dr is equal to zero. So we can go ahead and compute that. All right? If we want to go down here and we want to write or calculate the derivative of u with respect to r, we're going to rewrite u of r as I'm going to distribute the a and bring the r's out and raise that 1 over r to the negative 1. Only reason I do that is for me, I just enjoy taking derivatives of polynomials rather than derivatives of fractions. Okay, just a personal preference. You guys by no means have to do that. So we've got u of r is a over b times r plus ab times r to the negative 1. Okay, from here, let's go ahead and calculate our derivative. So the derivative of this, remember, I want to take the derivative of this guy and the derivative of this one. Okay, so dr of a over b times r plus d, the derivative with respect to r, of ab r to the negative 1, where I've split my function into two because I have this plus here, which says that I can do that and take the derivative separately. Okay? By working these derivatives out, remember the derivative of r is just 1, so you're left with a over b plus ab times negative 1 r to the negative 2. Okay? Negative 1 r to the negative 2. Now this comes from, remember, when we take the derivative, d dr of r to the n is equal to r to the n plus, or excuse me, r to the n minus 1, r to the n minus 1 times n. Okay? So, with that being said, we can rewrite this as a b plus, excuse me, let me erase that. Alright, get rid of this guy. That's going to be a over b minus ab as 1 over r squared. And this is equal to du dr. Now, I want to set this du dr equal to 0. Okay? So I know that 0 is equal to a over b minus ab over r squared. I'm going to go ahead and add this to this side. Okay? So I can rewrite this as ab over r squared is equal to a over b. Alright? Now, right off the bat, I see that my a's are going to cancel. They're both on the top and they're on opposite sides of my equal sign. Okay? That leaves me with, I draw this over here, that leaves me with b over r squared is equal to 1 over b. Okay? You can cross multiply here, however you'd like to simplify this, and you end up with r squared is equal to b squared, which implies that r naught is equal to b. Okay, so for that first part, you're going to end up with r naught is equal to b. Now, to figure out what the minimum potential energy is, all I need to do is take that r naught and plug it into my expression for u of r up here. So let's go ahead and do that. Okay, so this is going to be part 2 of this problem. We're going to say u of r naught is equal to u of d, because we know r naught is equal to b, which is that positive constant. Alright, which is a over b times b plus ab over b. Okay, you multiply this out, or simplify, excuse me, you get the u of b is equal to a plus a, which is equal to 2a, which is equal to u naught. So our final answer, 2a is equal to u naught, is our answer to part 2. Okay, now, if you guys want to work on part B here, it says sketch the net force. An important thing to remember here, you all, is when you're sketching a net force, remember that F is equal to the negative derivative of U with respect to R. Okay, remember that for part B. That's going to be very important. Okay, then you're just going to sketch the graph qualitatively, not quantitatively, as we don't know any numbers here. So you don't need to worry about doing anything quantitatively, no numbers, just sketch based on the tangent lines you see up in this graph up here. Okay, moving on to the last part, this C, D, and E are based on the assumption that the particle is released from rest at R equals R naught over 2, or B over 2. So we're saying it's released from rest here. Okay, that means the energy it feels at this point is all potential. It has no kinetic energy. So its maximum energy is going to be U of R naught over 2. You guys can use that to solve the rest of those problems. Okay. Overall, they're not that tricky. Once again, I'll be putting out a full solution to them later on in this class. Okay. All right. Hopefully that was helpful for you guys. I'm going to go ahead and start another video for the next one. I will post all 4 videos to our classroom once I get them done. Thank you all.